We studied first in this unit momentum at a specific time. P is equal to m times v. And then we follow that up with impulse, some qualitative implications of impulse, but also some quantitative impulse, the change in momentum over a period of time. What I want to look at today is the momentum not of an object at a particular moment in time, or not even the change in momentum of an object over a period of time, but what I want to look at today is the momentum of a system. So if 2 or 3 or 4 things collide with each other, I don't want to focus on the momentum of one object gaining or losing or whatever the case may be. I want to focus on the momentum of everything that was involved in that collision, the momentum of the entire system. But in order to do that, I have to assume, or I have to make this system what we call an isolated system. Do you guys know what an isolated system is? Yeah. System that what, sorry? System that doesn't rely on anything else? Sure, okay. System that doesn't have anything else? Yeah, system doesn't have any energy in or out. Good. In other words, like, let's put it in terms of maybe a little bit more concrete, a little bit more everyday working language. We don't have any external forces. There's no friction to take energy away from it. There's no wind to add energy to it. There's no external forces to do anything with the energy. If we have an isolated system and we analyze the entire system, then we say that the total momentum of that system will always remain constant. That's the same as the law of conservation of anything else. Remember in physics 20, the law of conservation of energy? Energy can't be created or destroyed. In other words, the total energy always remains constant. Here we're saying momentum can't be created or destroyed. In other words, the total momentum remains constant. Now, one object can gain and one object can lose. But if you look at the momentum of the system, it's going to stay the same. That is, if we have an isolated system. And an isolated system, remember, is that system where we have no external forces. You're right when you say no energy in or out, but it's more concrete to think of it as there's no forces, no external forces that are acting on it, because it's external forces that cause you to have energy coming in or out. Now, sometimes, like realistically, there are external forces. If we're analyzing a car crash, and by the way, we can use this, like police officers use this to analyze car crashes. But man, there's all kinds of external forces, right? Like as soon as these cars collide, there's friction. There's wind resistance. There's all kinds of stuff, right? All kinds of external forces. So what we usually do to make sure that we have an isolated system is look at the interaction, the collision that we have immediately before and immediately after. Like if I'm a police officer analyzing a collision, like 5 seconds after the collision, friction has played a big factor in this collision, right? In the analysis of this. But if I look at just after, like a fraction of a second after the collision's taken place, then friction hasn't really had a chance to do anything, right? So we'll call it an isolated system because all the friction's there. My collision has been before friction has had a chance to do anything. Got it? So look at just before and just after, and normally that's enough to make it an isolated system. Now, when are we going to use this? We're going to use this when we're analyzing a collision or an explosion. Collision, I think, is pretty self-explanatory what that means. Two things bang into each other, collide. An explosion, I have that in quotation marks because, well, it could literally be an explosion, right? A bomb explodes into pieces, or a rocket that NASA didn't design properly explodes into pieces. Yeah. But it could be more figurative too. Like it could be more figurative, like firing a gun. Fire a gun, bullet in the gun are effectively one object, right? Before I fire it. After I fire it, what happens? Gun goes one way, or sorry, bullet goes one way, gun goes the other, right? If I'm standing on ice and I throw a big heavy ball, medicine ball goes one way, You go the other way, right? Remember that scene from WALL-E? Where we have WALL-E has the fire extinguisher. Remember that? Fire's the fire extinguisher. All the powder from the fire extinguisher goes one way, WALL-E goes the other way, right? Like all of those are like explosions. They're not literally explosions, but they're like explosions where one object becomes two. If we look at the momentum immediately before and immediately after a collision or explosion, we get a good way to solve it, a good way to analyze it, using this new thing called the law of conservation of momentum. But, of course, what we've done till now is still valid. Impulse, change in momentum. How can we have a change in momentum when we're now saying the momentum stays the same? Well, because we were analyzing one object or the other, right? When two things collided, object A gained momentum, object B lost momentum. Now we're analyzing the system. Object A and B combined. Well, if you guys collided and you gained 10 units of momentum and you lost 10 units of momentum, then the total momentum stayed the same, right? We didn't gain or lose as a system. Impulse for you, but no impulse in the system. The total momentum in the system remained constant. Now, if you don't have to copy this next thing down if you don't want to. It's really up to you. I'm going to derive where this conservation of momentum law comes from using Newton's third law. Remember Newton's second law led us to impulse, the change in momentum of an individual object. Newton's third law leads us to conservation of momentum. So copy this down or not, it's up to you. I'm going to say from Newton's third law, look, F12 is equal to negative F21. Make sense? Object 1 applies a force on object 2. Object 2 applies an equal and opposite. That's why it's a negative. F12 is m times a. F21 is m times a. Let's replace a with delta v over delta t. Is that okay? Is it okay to do that? Sure it is. Yeah, sure it is. Now, I'm also going to cancel out the times here. How come? Two different times, right? Delta T1 and delta T2? Well, they're not really two different times. If object 1 is in contact with object 2 for 3 seconds, then object 2 is in contact with object 1 for 3 seconds, right? So the times are the same. Even though they're called something different, it's the same value. M delta V is equal to negative M delta V. Look at that. Remember we said the impulses are always equal and opposite? M delta V is equal to negative M delta V. The impulses are always equal and opposite. Now, what we can do here is replace delta V with VF, V2F minus V2I. V1F minus V1I. Again, you don't need to be able to derive this. You should know that it comes from Newton's third law, but in terms of actually deriving it, I'm not going to ask you that question on a test. I don't know about you, but like when I was in high school, and we never used to really have to derive things in physics class in high school, but in math class we had to all the time prove things and derive. Do you guys have to do that? I hated those. I hated them. I felt like I was terrible at it back then. Maybe I'm still not great at it, but better at it than I was then. I'm not going to make you do this. But again, just know where it comes from. Know that it comes from Newton's third law. Okay, I'm going to distribute the M2 here. M2 times V2F minus M2 times V2I equals negative M1 V1F plus, right, negative times a negative is plus M1 V1I. Now, if I change the order of this, then this is what I end up with. M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. All of that to get to this. What does this tell us? If two things collide, the momentum of object 1 before the collision, M1 V1I, plus the momentum of object 2 before the collision. In other words, the total momentum of the system before the collision is equal to the momentum of object 1 plus the momentum of object 2 after the collision. In other words, the total initial momentum equals the total final momentum. Does that make sense? Really, what that boils down to is this. Pi equals Pf. That's the big takeaway from that big derivation. That's what you got to remember. Pi equals Pf. Pi is the momentum of each object combined before. Pf is the momentum of each object combined after. What principle, what physics principle would this be? Pi equals Pf. The total initial momentum equals the total final momentum. Look at your sheet or look at the backboard there. This is like the easiest one ever. What is it? What is it? No? Yep. Nope. I thought it was the easiest one ever. Yep. Fourth, conservation of momentum. Right? This is conservation of momentum principle 4. Okay, it's exactly what it says on the list of physics principles. Okay, let's do an example and then I'm done with you guys for today. How about that? I am so done with you guys after this question. 1,500 kilogram car travels north at 20, collides with a 1,700 kilogram car traveling south at 21. I want to draw attention to the north and south here because, man, if I don't, I know I'm going to miss that. I'm going to forget to make one of them negative, right? And when we got north and south, one of them has to be negative, probably the south. The two cars entangle after the collision. So that means they head off as one object after the collision. We want to find the velocity of the wreckage immediately after the collision. Now, understand that each of these cars experiences a change in momentum. We could analyze car number 1. Don't write this down, okay? We could analyze car number 1 using impulse, or we could analyze car number 2 using impulse. But that's perfectly valid. But you'd have to do car number 1 or car number 2. Got it? What I want to do in a context of a collision almost always, even though this is valid, what I just showed you, what I want to do almost always is analyze the system. If I'm going to analyze the system rather than an individual object within the system, then I'm going to use principle 4, which is conservation of momentum. Pi is equal to Pf. Let's write down some givens here, okay? I'm going to say the 1,500 kilogram car is car number 1, and the 1,700 is car number 2. I'm going to say M1 is 1,500 kilograms. Something's 20 meters per second. What is that? It's a velocity, right? Is that V1 or V2? Velocity 1 or velocity 2? 1. Good. It's car number 1. Is that initial or final? Before or after? I or F? Somebody said it? Initial. That's V1I. What else we got here? 1,700 kilogram car. I'm going to call that M2. That's the second object. Now I got another velocity here. It's 21 meters per second. What is that? 21 meters per second. Is that V1 or V2? 1 or 2? What is it? Yeah, that would be V2. Is that V2I or F? You're thinking the same thing as I am now, aren't you? What is it? Yeah, that's V2I. Good. We're missing something, though. Yeah, I'm going to make that negative. I'm likely to catch that because I circled the south there, right? And head off is one, got nothing else. What am I looking for? Let's call it VF. I'm not going to bother calling V1F or V2F because they're together, right? The two cars are one. They've embraced. So now they are one. They're one with the other car. Now, I'm going to use this new thing, this newfangled conservation of momentum thing. I could do impulse for car 1 or impulse for car 2. That would be okay, but this is better. I'm going to do conservation of momentum for the system. Just before and just after, so friction or any other force doesn't have a chance to come into effect, right? In other words, so that we have an isolated system. How many objects do we have before this collision takes place? How many things do we have? 2, right. So let's say M1 V1I plus, not times, M1 V1I plus M2 V2I. We got one term for each object that we have. We just add them together. Total momentum is, add the momentum together. How many objects do we have after the collision? Well, remember, the two cars have embraced. The two cars have become one. So how many objects do we have? Yeah. I'm just going to call it M total times VF. Right? M total being, what? What would it be, 3,200 kilograms? Because that's the mass of our wreckage now, right? Don't try to rearrange this. Just sub your numbers in and then rearrange it. M1 is 1,500 times V1I. M2 is 1,700 times V2I. The total mass is 3,200 times VF. $1,500 times 20 is 30,000. $1,700 times negative 21, negative 35,700. Combine those two numbers on the left side. Negative 5,700. And then we're going to take 3,200 over by dividing. Gives us negative 1.8 to 2 digits. So car going north, car going south, they collide. Where does the wreckage go? South. Right? Why does it end up going south? Well, because the car going south had more momentum, right? It had a mass of 1,700 and a velocity of 21 meters per second. It clearly had more momentum, so who wins? The one with more momentum wins, right?